Drag force is a fundamental concept in physics that explains how air and other fluids resist the motion of objects moving through them. Understanding drag force helps us explain everything from why parachutes slow our fall to how engineers design fuel-efficient vehicles. Drag force is a resistive force that opposes the motion of an object moving through a fluid. A fluid can be either a liquid like water or a gas like air. This force always acts in the opposite direction to the object's velocity, trying to slow it down as it moves through the fluid medium. Fluids create resistance through two main mechanisms. First is pressure drag, which occurs due to the difference in pressure between the front and back surfaces of the moving object. Second is friction drag, which is caused by viscous friction between the fluid particles and the object's surface. Both types work together to oppose motion. The drag force equation is F sub d equals 1/2 rho v squared c sub dA here. F sub d represents the drag force. Rho is the fluid density, v is the velocity of the object, c sub d is the drag coefficient, which depends on the object's shape, and A is the cross-sectional area perpendicular to the flow. Four main factors affect drag force. Velocity is crucial because drag increases with the square of speed. Shape matters because streamlined objects experience less drag than blunt ones. Cross-sectional area is important as larger areas facing the flow create more resistance. Finally, fluid density plays a role since denser fluids create more drag. The drag coefficient, represented as c sub d, is a dimensionless number that quantifies how streamlined an object is. It depends purely on the object's shape and surface properties. Lower c sub d values mean the object is more aerodynamic and experiences less drag, while higher values indicate poor aerodynamic performance. Let's look at some real examples. A streamlined body has a drag coefficient of just 0.04, making it extremely efficient. A sphere has a coefficient of 0.47. A flat plate perpendicular to flow has 1.28, and a parachute has 1.4, which is intentionally high to maximize resistance. Air and water create very different amounts of drag. Air has a density of approximately 1.2 kilograms per cubic meter, resulting in lower resistance. Water, however, has a density of about 1,000 kilograms per cubic meter, making it roughly 800 times denser than air. This means water creates much stronger drag forces on moving objects. Drag force is proportional to the square of velocity, written as F sub d is proportional to v squared. This quadratic relationship has significant implications. For example, if you double your speed, the drag force doesn't just double, it increases by a factor of 4. This is why high-speed vehicles require much more power to overcome air resistance. Terminal velocity is the maximum velocity an object reaches when the drag force equals the gravitational force pulling it down. At this point, F sub d equals F sub g. When these forces balance, the net force becomes 0, acceleration stops, and the object continues falling at a constant speed. Drag force has numerous practical applications. In vehicle design, aerodynamic shapes reduce fuel consumption by minimizing air resistance. Skydivers use parachutes that maximize drag for safe landing. Aircraft must carefully balance lift and drag forces during flight. Even swimmers optimize their body position to minimize water resistance and improve performance.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.